Hi, this is Dr. Nerz. I'm doing a little video boost on Sunday night video boost 6. I wanted to talk a little bit about the quiz because some people had some trouble integrating double bond stereochemistry in with asymmetric carbon stereochemistry, which is something you really need to know how to do. So supposing I had to write all the stereoisomers of the following compound, not to make it too much like what we did in class. So say you had that and you had to write all the stereoisomers of it. Well, this would really have two what I call stereocenters. It has an asymmetric carbon and it has a double bond that can have Z or E. So this is not dissimilar from what you did in class. Probably the easiest way to do this is to use the Fisher projection, although it's not the only way. So for example, if I chose to use a Fisher projection, I would project this center. I would draw in the groups attached to that center, which are a chlorine, a methyl, and an ethyl. And if you wanted to, you could draw the ethyl as CH2, CH3. There's nothing wrong with that. And then I would bring myself down and draw the double bond, probably as it is written. Of course, this double bond has no stereochemistry. So which one have I drawn? Using my priority system, this is 1, this is 2, and this is 3. It looks like it's S, it's really an R. This, if you draw the hydrogens in properly, is an E. So what are the other stereoisomers? The other stereoisomers are the R, Z, the S, E, and the R, E. So if I was going to draw these very quickly, I would draw the Fisher, I would fill in these groups, and then draw the mirror image. Okay, what is this one? This is the S, but notice it is still E. And that's why I gave you the little hint. I said when E looks in the mirror, it sees E. It doesn't see Z. A lot of people have this idea that the mirror image of Z is E. That's not true. This is the only part that's really affected by stereochemistry. And the overall molecule is asymmetric. This just becomes one of the groups on this, but it does have its own stereochemistry. So what else could we draw? Well, for example, we could draw the R. So I'm just keeping everything else the same. Z, which would look like this, okay? This is the RZ. Or, right, one more I can draw. So I'm erasing for space here. I could draw the S. Z. Let me double check this. 1, 2, 3. It looks like it's R. It's really S. So there's 4 stereoisomers. What are their relationships? Okay. R, Z with S, Z are enantiomers. R, E with SE are enantiomers. All other relationships are diastereomeric. So for example, if I compared SZ with SE, while it does seem reasonable to call them geometric isomers, the term diastereomer, even though it overlaps with the optical isomer category, is a correct description because diastereomer refers to anything that is a stereoisomer but is not a mirror image. So it actually encompasses geometric isomers. How much time do I have?
You're at 4:40.
Okay, so the other thing I wanted to mention was, and there are several diastereomeric relationships there. A lot of people have been asking me about 3 centers, and I just wanted to bring that up. What would happen if you had 3 centers? Can you have a meso? And this is kind of a peculiar situation. So there's a problem in your book like this, where you have an alcohol, a triol rather, something that's 3 alcohol groups. And it's really best dealt with on a Fisher projection, okay? So the weird thing about this structure is that this compound is a meso, because you can split it right here, right through those atoms, and the top is the mirror reflection of the bottom. Now I taught you how to be good meso detectives, and what I said was, where you have clear-cut asymmetric carbons, one should be the mirror reflection of the other in terms of assignment, absolute configuration. So this is 1, 2, 3, it looks like it's R, it's really S, I guarantee you this is R down here. So this is reflecting that. That is a meso compound. It is possible, when you have an odd number of atoms, to have a center that is a kind of a peculiar asymmetric center. This is called a pseudo asymmetric center. And I'm going over this simply because people have been asking me about it. I wouldn't expect someone to be able to name that or assign that center, but to recognize that this is a meso. It meets the requirements of a meso. What is a meso? A meso has asymmetric carbons, and it is superimposable on its mirror image. And this is superimposable on its mirror image. So what other mesos could I come up with for this structure? I could get this. And again, Latin has a couple problems like this that are not bad to do. It's a little messy there. Okay, why is this one also a meso? And why is it different? This is a meso. It's also SR. But notice the OH is on the other side. And to go from this one to this one, you actually have to break bonds. And this one is not superimposable on that one, so you can give it a try. So there's actually 2 mesos. And as I recollect, there's only 2 other stereoisomers. One is the, what we'll call the SS, which is this one. I'm keeping the middle the same. And in these cases, changing the middle doesn't change it, but you should play around with it. This is the SS. And then there's a similar, I'll draw the mirror image, there's an RR. But in our review tomorrow, and maybe in class a little bit, we'll do some more work on these. I'm not planning on giving you anything incredibly complicated from a meso perspective on this test. Okay? So this one is the RR. And again, you can't really assign that middle center. So these 2 guys would be enantiomers. Then what would their relationship with these be? All those relationships are diastereomeric. All of them, okay? Because RSS is the diastereomer of SR, even if you can't assign that middle center, okay? So you would find in this case there's only 4 stereoisomers, because this is, when you draw the mirror image of this, it's superimposable. When you draw the mirror image of this, it's superimposable. And then you find when you play around with these, with this middle center here, you get the same thing back. It's kind of interesting from a symmetry perspective, and it's a really good problem to do with models. For this week, for Monday and for Friday, I would recommend that you bring your models in. Again, we have a review tomorrow from 5 till 6, and then from 6 until 7 p.m. Thank you. Bye.